Alright, for the last section here on section 16.4, we're going to talk about calculating and calculations that involve colligative properties. We're going to talk about two new concentration units, ways to express concentration. One is called molality and the other one is called mole fraction. So these are two new concentration units, in addition to percent by mass, percent by volume, and molarity. Molality here is the moles of solute divided by kilograms of solvent. This would be something you would definitely want to include on your green card. Make sure that you are paying attention to molality not being the same as molarity. Molarity is usually abbreviated a capital M, whereas molality is usually abbreviated a lowercase m. That's italicized, sometimes written as a cursive M if you're going to handwrite it. So here's how we could use molality. This is how many grams of potassium iodide must be dissolved in 500 grams of water to produce a 0.060 moles Ki solution. So molality is moles of solute divided by kilograms of solution. So we can set this up as 0.06 molal equals, we're looking for moles of solute divided by 0.5 kilograms of solution. And that gives us 0.03 moles of potassium iodide. And then we would need to convert that to grams of potassium iodide using the molar mass. The other unit of concentration that we're going to talk about is mole fraction. It's a ratio of moles of the solute to the total number of moles. So if we have N being number of moles, so the number of moles of A divided by the total number of moles gives us the mole fraction of A. And then the number of moles of B divided by the total number of moles will give us the mole fraction of B. Mole fraction is a dimensionless quantity. It's a little scary because that means it is a naked number. And normally we don't have those, but it is because it's moles divided by moles, and so there's no units for mole fraction. If you add up all the mole fractions together, it should equal to be 1. So it's like a percent almost, but we're not converting it to the percent. So here is an example calculating mole fractions. What is the mole fraction of each component of ethylene glycol and water? We have 1.25 moles of ethylene glycol and 4 moles of water. So calculating the mole fractions, we see here the total moles is 5.25 moles. And so the mole fraction of ethylene glycol is the 1.25 divided by 5.25. which gives us 0.238. And then the mole fraction of water would be the 4 moles of water divided by the total number of moles again. And then we come up with 0.762 as the mole fraction for H2O. So if you were to add those two mole fractions together, they would equal 1. Molality is the concentration of unit that is related to the colligative properties of freezing point depression and boiling point elevation. Generally, the amount of freezing point depression and boiling point elevation is usually quite small. You need a pretty accurate thermometer to be measuring those temperatures. But we can also come in and calculate the amount of colligative property, what we call the colligative effect, if you know the molality of the solution. The amount of freezing point depression, abbreviated delta TF, and the amount of boiling point elevation, abbreviated delta TB, those are directly proportional to the molal concentration, assuming the solute is molecular and not ionic. If it's ionic, we have to take into account the number of particles. So we'll have to keep that in mind if we're doing an ionic solute. Going back to looking at a phase diagram, this green line represents the phase diagram of pure water. So areas that contain solid, liquid, and vapor, just like a regular phase diagram. But the vapor pressure is lowered when we have a solvent. So this purple line represents the lowered vapor pressure, which shows us that the freezing point is going to be lower and that the boiling point is going to be higher. Here we see the boiling point being 100 degrees Celsius for pure water and a point higher depending on what concentration of molality of our solvent is. So if we add a proportionality constant, the freezing point depression, delta TF, is a freezing point constant times the molality of the solution. This is assuming that we have a molecular solute. So we look up this freezing point constant. This is a constant that is for each different solvent. So we look up the freezing point constant of water times the molality of the solution. If it's ionic, we would also then multiply by the number of moles of ions present. So if it is an ionic compound. If it's molecular, you don't have to do that part. Not surprisingly, the boiling point elevation equation looks very much like the freezing point depression equation. We're going to have a different constant, this constant for the solvent, like water, we'll look that up, times the molality, times the number of moles of ions if we have an ionic solute. Here are the values of Kf and Kb for some common solvents. Notice water is down here at the bottom. 1.86 is the freezing point constant for water, and 0.512 the boiling point elevation constant for water. So here's an example calculation. What is the boiling point of a 1.50 molal sodium chloride solution? So we know that the change in the temperature of the boiling point is the Kb times molality times the number of moles of ions, right? So how will we do that? First we need to look up the freezing point, the boiling point elevation constant for water, and that's 0.512 degrees Celsius per molal times the molality, 1.50 molal, times the number of moles of ions. Sodium chloride is going to dissolve and give us 2 moles of ions. So the change in the temperature of the boiling point is going to be 1.50 0.54 degrees Celsius, which means the new boiling point would be 101.54 degrees Celsius, adding to the original boiling point of water being 100 degrees Celsius.